Well, how did you do? Let's see how to answer this. First of all, it's always helpful to draw the triangle by putting in the vector components. And notice that this very clearly shows us that the x component has to be negative and the y component has to be positive. And that eliminates most of the possibilities without us doing any calculation at all. Furthermore, notice the vector is drawn in roughly the right direction. And notice that the y component definitely has a bigger magnitude than the x component. Well, that eliminates most of the other options. And so we've already come up with the correct answer without doing any calculation at all. That might feel like cheating to you, but really you should be doing that sort of analysis before you reach for your calculator, so that if you punch something into your calculator wrong or drop a negative sign, you can catch yourself. But let's actually calculate it. Notice that the x component forms the opposite side to the 30-degree angle in the triangle. And so we're going to calculate the x component using sine, where notice I've put the negative sign in by hand because I know the x component has to be negative. And similarly, the y component is the adjacent side of the triangle, and so we're going to calculate it with cos. Here are a number of vectors, and we know them in component form. Now, some students seem to think that if you have a vector in component form, you need to find its magnitude and direction. Really, you don't. Unless there's some specific reason for needing the magnitude or direction, you might as well leave it in component form. Most of the time, component form is actually the most convenient form to have a vector in. However, sometimes you do need to know the magnitude and direction, so let's see how you do it. And it's just trig that you've probably learned before. So first I'm going to find a with no vector symbol. So remember that what we mean when we write the a with no vector symbol is that we want the magnitude of a. And you know how to do this because here's a triangle, and you know this side is 4 and this side is 5, and the magnitude of a is just the length of this side, and you've known Pythagorean theorem for years and years and years. Now, the other thing we need is an indication of direction, and the easiest thing is just to get this angle here, because we usually state the direction of a vector in terms of its angle from the x-axis. So I'm going to call this theta a, the angle for the vector a. And what we know is that tan of theta a is the opposite over the adjacent. So that would be ay, the y component, over ax. There we go. And so that tells us that we can find theta a just from the inverse tan of ay over ax. And so that's 5 over 4, where those are both in meters, so the meters are going to cancel and I don't need to worry about them. And that's about 51.3 degrees. Let me just do that again with b. And then I'll define theta b to be here. So by convention, angles counterclockwise from the x direction are positive, and so this will be a negative angle by convention. And we're all done. Now we know both of these vectors in terms of their magnitudes and directions. So let me remind you that the vector is the arrow. The components don't define the vector, nor does the direction, because we can define a new set of axes oriented, say, at 45 degrees to the original ones. And now this vector is at a different angle from those axes. Now its magnitude hasn't changed, but to describe the direction that this vector points in, we now have to come up with a new angle. Well, you can see from the 45 degrees and that the original angle from the original x-axis was 26.6 degrees, that this is now 18.4 degrees below that new x-axis. And we could now use the procedures we just found to find the new components of this vector in this new coordinate system. But it's the same vector. We're just expressing it with reference to a new set of axes. Okay, the camera pans back to reveal that the lemon thrower was standing on the side of this hill with a 20-degree grade. And so now let's find the velocity vector again, but it might be convenient to work in axes that are referred to the hill. So just for sake of argument, I'm going to put my x-axis pointing downhill because I'm allowed to do such things. And let's go and find the vector in these coordinates. Because now, if you think through the geometry of this, here's a perpendicular to the hill. And the thing to notice is that this angle in here is 20 degrees. And that gray line there is parallel with the y-axis. And so our v, if we slide our v over to where the axes are and do that geometry, we see that this angle here is 50 degrees. And so now in our new coordinate system, we've got this situation. There's our v, here's our vx, here's our vy, and this is 50 degrees. And so we can do it all again, and I'm just going to take a slight pause to do that. Okay, so I've carried out the trig, and I've actually deliberately made an error, because look, vy is fine, but look at this vx, and compare that vector with these axes. Its x component is back in the negative x direction. So I'd better be careful here. I should now write this as negative 11.5 meters per second I plus 9.6 meters per second j, where now, under these axes, my I points this way and my j points this way. I'm just going to finish by briefly talking about what are and are not valid vector algebra operations. We've seen addition of vectors, and we know how to think of them graphically as putting one vector head to tail with the other, and we know how to do them algebraically. It can be summed up as by saying we add the x components to each other and we add the y components to each other. And we know that to subtract, we just have to take the negative of one of the vectors. We've also seen how to multiply a vector by a scalar, and it can be summed up as saying that we simply multiply each of the components by the scalar. And note that since division is just multiplying by the reciprocal, we also know how to divide a vector by a scalar. However, there's no such thing as division by a vector. Maybe in class we'll have time to discuss why, but the point is that there's no meaning that can be attached to either dividing a scalar by a vector or dividing a vector by another vector. And so both of these expressions are meaningless. If you ever come up with an expression that has a vector in the denominator, you've definitely done something wrong. Back up and figure it out. What about multiplication of a vector by a vector? Well, there's sort of such a thing as multiplication of a vector by a vector. This expression is meaningless. Well, maybe. There's a thing called a tensor product that we'll never need to deal with in this course, and in fact, most of you will probably never encounter it, and some people write it this way. But if you write this expression down, for our purposes, we should just say this is meaningless. However, there is a thing called a dot product, which we'll encounter later in this course, and there's another thing called a cross product, which we'll encounter in Phys 1204. These are not really multiplication in the usual sense that you're used to, but in certain ways they behave like multiplication.